Hi, I'm back. Fitting and turning level 3. We're busy with the ISET project, but at the same time, we're learning about the lathe. Just a recap on last time, we got as far as setting up our cutting tool to center height. We've clamped our workpiece and we are going to perform a facing process. I made sure that my feet is in the right direction. Cross slide going in. My cutting fluid. Just a recap, why are we actually using cutting fluid? And what is cutting fluid? There's different types of cutting fluids. Neat oil, or as in this case, soluble oil. And the main reason for using a cutting fluid is to keep our cutting tool cool. The moment our cutting tool overheats, it becomes blunt and then it will stop cutting. So as to keep our cutting tool cool. Secondly, it gives a nice finish. It allowed me to use higher cutting speeds and feeds. Because of that, we can increase our rate of production. As well as it washes away the cuttings, remove the cuttings out of the way. And that are the reasons why we're using a cutting fluid. So you can see before I'm starting to do my machining, I switch on my cutting fluid. I don't want to fiddle around here while I'm machining. And now I'm going to start doing my machining process. Facing, I'm just cleaning up. I'm not taking a big cut. It's just cleaning up. About 0.3 of a millimeter. You can see I'm standing ready. My hands are not close to the moving parts, but I'm standing ready in case I have to stop anything in emergency. I can stop. I give my full attention to what I'm doing. I'm going to keep on machining till I'm just past center. Disengage, switch off, move away. And there you can see, nice and straight with a nice smooth finish. Now with this workpiece, remember I want to cut it at least 105 millimeter long. That's going to be my next step. To a diameter of 28. Now why 105? Because I want to cut it slightly longer so that I can machine it off to bring it exactly to 100 millimeter. Now referring to the drawing, you'll see that all my tolerances are 0.1 of a millimeter. Now 0.1 of a millimeter, that's a very big tolerance. Not difficult to obtain. With these machines, it's quite easy to obtain an accuracy of plus minus 0.01. So 0.1, easy to obtain. So I faced, and now I'm going to drill a center hole there. Now why do I drill a center hole? It's because I'm going to clamp the workpiece over there. And because it's sticking out quite far, you can have an effect where the workpiece will bend away from the cutting tool. If it's a larger diameter and it's more sturdy, it will not, but in this case, it might bend away. Now, what do we mean by that? Let's take this ruler. If I exert a force there, what do we see happening to the ruler? It bends away. So you'll find you'll have a larger diameter on that side, and as you're getting closer to where the chuck is, it will become more and more accurate. So to prevent that from happening is I'm going to support the workpiece with my tailstock and a center. But I first have to get a center hole. And for that, I'm going to require a center drill. And there's my center drill, already clamped to my chuck. There's a center hole that I've pre-drilled. And how deep am I going to go in to my workpiece? This one is slightly too deep. Normally, we'll go about halfway up the taper, right there, more or less. That's about how deep I should go with my center. As I say, this one, slightly too much, but it's still all right. I'm going to remove my revolving center by just turning the spindle back, and at some point it will force out the center. Turn it forward again and fit my center drill. Now I'm going to let my workpiece stick out long enough for where I'm going to machine. So I'm just going to use a ruler. Remember, I'm going to machine for at least 105. But if I make it exactly 105, it means I run the risk of letting my cutting tool run into my chuck. And I don't want that to happen. So I'm going to move it back, say about 130, plus minus 130. Clamp. Put my shoulders behind it. That's it, nice and tight. Bring my center drill closer. Be careful not to bump your center drill into the workpiece. Tap it slightly. If you bump it, it's high-speed steel, it will break. Bring it close to your workpiece. Now remember, the center drill, the diameter in the front is quite small. And because it's so small, you have to use a higher cutting speed. Now if you remember the basic rules when it comes to machining is the smaller your drill bit, the higher your cutting speed. Larger your drill bit, slower. Harder the material, slower, softer, faster. So in this case, I'm going to push up my speed to about 755. Now here, I quite often see students hammer these things because they don't want to go into gear. Remember, it's not a car that got a clutch. You can only change the gears if the machine is at a complete standstill. And over and above that, quite often you will find that it doesn't want to go into gear. So then it's a very simple process. All you do is you take the chuck, you move the chuck around, and you'll find it will slot into gear easy. Don't force it, you will break it. So just move your chuck and you'll find it will go into gear. At the moment, I've set the speed to 755. I'm going to use cutting fluid because I don't want to burn out my drill bit or my center drill. Put my cutting fluid, get it into place. I don't fiddle around with it while I'm machining. Now you'll find with the center drill, I'll go in, slightly back, in, slightly back, slightly back. And remember, only halfway up the taper. And there's my center hole. Why did I go in and out, and not just all the way in at one time? Very simple. You have a build-up of cuttings. And that build-up of cuttings can jam between your drill bit and the work, causing the drill bit to shear off. So take it forward, backward, slightly more, and obviously every time you go in, slightly more in. So there is my center hole. Now you'll find that I'm not removing the workpiece, and I'm not going to remove the workpiece again till such time that I'm ready to do the other side. The reason for that is I'm working with a 3-jaw chuck. And one of the disadvantages of a 3-jaw chuck is that once you remove the workpiece, you lose your centricity. And that means your work is not going to be accurate. So I'm going to leave it till I've completed my whole machining operation. Fit my revolving center. Now what does that revolving center do now? Remember, there's a center hole. And what that center hole does, if that's my work, and the center is there, when I'm machining now, it will prevent the work from bending away from my cutting tool. So it's support. So I'll use a revolving center or a dead center, but in most cases we'll use a revolving center to support the workpiece at the end, preventing it from bending away. So here's my tool. I'm just going to double check that it's still centered. Yes, it's centered. I'm going to put my cutting tool straight, because what I'm going to perform now is parallel cutting. At the moment, this workpiece is plus minus 30 millimeter. I want to make it exactly 28. Remember, we got a tolerance of 0.1. So it means it can be 29.9 or 27.9, because remember, it must be exactly 28. So I can have it between 27.9 and 28.1. If it's in between, I'm fine. Obviously, I will try to get it exactly 28. Right, so now I'm ready to do my parallel turning. And what I'm going to do is, I'm going to take a cut to clean up. Plus minus, remember it's 30 plus minus 30 now. So I'm going to take a cut of about, say, 1.5 millimeter to clean up so I can get an accurate measurement, and then take a final cut up to 28. I'm going to just make sure that my feed direction is correct. And I can see my feet is still on the cross, which is dangerous because it can cause me to run into my work. Make sure my feed direction is correct. Correct. I'm going to take about a 1 millimeter, no wait, 0.75 of a millimeter cut here, maybe 1. Yeah, 1. But you'll find what I'm going to do is I'm going to turn my collar here back to 0. Be careful not to move, so I'm going to put it exactly on 0. And you've seen that I'm taking my cross slide in, not out, in to do the cut. By taking it out, you'll have backlash and play, which is going to cause a lot of problems for you. So I took it in, take up all the play, 0 my reading, and now I'm going to take the cut. I'm just going to slow down my speed back to 480. Use my cutting fluid. And I'm going to cut for plus minus 105 millimeter. Concentrate on your work. If anything goes wrong, don't panic. Just stop. And if, hit the emergency. Don't try to remove the cuttings by hand. Don't try to take any measurements while the machine is in motion. Now remember, I zeroed it here, so I can turn it out. Take a rough reading, remember, just plus minus, I got it at 110, which is fine, Now I'm going to measure with my micrometer. Now remember, with a micrometer, you first have to calibrate it to make sure that it is accurate. This specific micrometer will come with a test piece of 25 millimeter because it can measure from 25 to 50. I'll clean the surfaces here, no dirt. Clean the anvil, clean the spindle, put my test piece in there, close it, and remember, you never turn on the thimble, just on the ratchet. The moment the ratchet starts slipping, you can take your reading and you can see that the reading is exactly 25 millimeters. So it means that this micrometer is accurate. Now I can take my measurement here. And the reading will be between 28 and say 29.5, somewhere there. Make sure you're nice in the center. Turn on the ratchet. Nowhere else, just on the ratchet till it starts slipping. And I can take my reading. And at the moment I can see that my reading is 28.94. 97, yeah, sorry, 94. My eyes are not that good. 28.93. So it means I have to remove 0.93 of a millimeter. Now this dial here, every line here represents 0.05. Now don't assume that it's always 0.05 because it varies from lathe to lathe. This specific one is 0.05. So it means one line, if I move it one line, it will remove 0.05 of a millimeter. So I have to remove 0.93 of a millimeter, divide by 0.05. I have to remove 18.6 lines. Make it 19 lines. That's how much I have to remove. Just double check. Because we can't put material back. We can rather still remove, but we can't put back. Once you've removed too much, that's it. All right. My mistake is 29.43. 29, so it's 1.43. See, it's always good to check. I must remove 29 lines. Now, if you can remember, I had my cross slide on 0. So I'm going to take it back to 0. Because 0 is my place where I'm just on the work. So I must remove 28 lines. So there's 10, 20, 25, 26, 27, 28. That's it. See, I'm giving a little bit more of cutting fluid because my cut is 1.43 millimeters, quite a big cut for this machine. So I'm supplying a little bit more cutting fluid to keep my tool cool. I don't stop, I just do my whole cut in one time so I don't mess up my finish. Get ready to disengage. Disengage, and my work should be exactly 28 millimeter. Turn on a ratchet. It's 28.03. It's inside the tolerance, so I'm going to leave it as such. Right. Now, very important, I find a lot of students now want to start removing the workpiece. If you move it, you lose your centricity. I find my finish here is not so good. Maybe I should have taken the last cut slightly smaller, but I'm going to leave it as such. The next thing I have to do is I have to put on a chamfer here. Now, what's the reason for a chamfer? There are many reasons. One is purely aesthetics. It makes it look a little bit nicer. Another reason is to break the sharp edge so it doesn't cut you. Another reason is if it's a pin that have to go into a bush, the chamfer will aid in sliding it in better, give a bit of a lead. So cutting the chamfer, I can use the same tool, or I can use this tool that's already at 45 degrees. Make sure that you are at center height. So I'm just going to break that sharp edge. And there's my chamfer. I've given it a nice break there, so it's not so sharp anymore. Sometimes they will tell you exactly what size the chamfer have to be. In this case, I've just broken the edge there with about 0.5 millimeter. Right. So let's quickly recap. What have we done? We have turned the shaft parallel down to a diameter of 28 millimeter. We've drilled a center hole to support it at the end to prevent it bending away. We took a rough cut, measure, we took a final cut, and the diameter is down to 28.03, which is well inside the tolerance. A reminder, at the bottom of the screen is some information and contact information. Feel free to contact us. We'll assist you where we can.